Hello students, in this video we shall see what are all the various kinds of graphs which are present in 12th physics CBSE. Graphs and figures, and especially ray diagrams along with the circuit diagrams in semiconductors chapter, this itself will come for 7 to 10 marks, and questions based on these are very easy to solve. To solve graphs, let's try to understand some basics. First one, if we are given a graph, say a very easy graph, voltage current graph, in this there is another variation, current voltage graph. What is the difference between two? It appears it is the same, but the primary difference is in case if they ask for slope, the slope here refers to resistance, because slope always is this parameter y axis by x axis. Okay. So, here the resistance is V by I. You are given two curves A and B. In this, curve A has more slope. Okay. So, meaning let us say there are two resistors A and B. In each of them, this is the path. If they ask you which one, A or B, has more resistance, the answer is A, because we will find the slope value. Slope value obviously is more for A. Okay. Slope is more for A and less for B. So, A has higher resistance value, and in case if we find the slope in this graph, that will give 1 by R value. So, this is a very important thing, how slope works and what is the relation between these two axes and slope. And we know differentiation is nothing but finding the slope for a curve. If it is a straight line, the slope value is constant, but if it is a curve, the slope varies at every point. So, how do we find it? We differentiate y axis with respect to x axis. In this case, it is resistance and integration. So, if we are given a graph, if we differentiate, we get the slope. If we integrate, we get the area under the curve, correct. So, that is the equivalent of multiplication. So, differentiation is the equivalent of division V by I, which is finding the slope. Integration is the equivalent of multiplying these two values V and I. That in this case V and I will give power, which is in terms of watts. A graph, but this is important. This gives the direction of field lines inside an electric field. So, from positive charge, the topmost one is a positive charge. If you observe, the field line direction is in the outward direction. The second one is a negative charge, the field line direction is inwards. So, here the third one, there are two positive charges. So, both of them will not touch each other, the lines from each will not touch each other and they go in the outward direction. Similarly, the lines in a positive and negative, actually they attract each other. So, the lines from positive go to negative charge. This is important. And the voltage and current, the electric field and potential inside shell is very confusing for most. It is actually very simple. Idea 1, on the surface of the shell, okay, on the surface of a charged shell, the electric field and the potential both are non-zero values. The electric field and the potential are actually maximum in the surface of the shell. The value for electric field we know is inversely proportional to R square, and the potential is directly proportional to, inversely proportional to R, and these are the values outside. But if you observe inside, the electric field inside a charged shell is 0. That is why if you observe, it is 0. So, that is the graph. If you observe, the electric field value is 0 here, but the potential inside a charged shell is always constant. It is same as the value which is on the surface of the shell. So, if you observe, the surface of the shell as well as the potential inside the shell, both are same values. And this is another important graph. This gives E versus V. Okay. So, E versus V graph, E is this, the V point is not very visible in the graph, I am just tracing. E is this, and V, which is inversely proportional to R, is this. So, until it reaches 1, yes. So, I have tracked both of them. So, the first one is E, the second one is V. The third graph, this is not again a graph technically, but again is important. The equipotential surface of a point charge. Surrounding a point charge, the equipotential surface, it is concentric circles, whereas if you consider a dipole is nothing but something which has a negative charge and a positive charge. So, we may think that the circles surrounding the dipole, they are concentric. No, they are not concentric circles. They are actually crowded here, and they are the distance between them is more in this region. So, if you observe again for a positive charge, it is crowded here and it is relaxed here. If you consider two positive charges, the equipotential surface in between them, the gap is large, and on the other side the gap is small. So, this is how you should draw. This is the difference between a dipole, which is nothing but a point, positive and negative charge, and between two positive charges. Now, this is important graph, the limitations of Ohm's law. The first graph, which is a straight line, but if you observe at the top, the graph is expected to go in a straight line. The expectation is a straight line. Let me draw it again. The expectation is actually a the expectation is a straight line. However, it actually bends the other way. That is because of the heat produced in the wire due to the high current. So, at that stage, current and voltage will not be linearly proportional. And the second one, it is very simple. We know that in semiconductors, the one is forward bias and reverse bias. Again, it is not a straight line. So, what is the limitation of Ohm's law? Meaning, in what situations Ohm's law will not be obeyed by the circuit. So, Ohm's law will not be obeyed by semiconductors. And third one also, in this region, we have three regions. Initially, when it starts, it actually obeys Ohm's law because it is a straight line, but as it progresses, it becomes non-linear and then negative resistance region. So, this example is gallium arsenide. So, these three are the conditions in which Ohm's law is not obeyed. The next one is temperature versus resistivity, again very important. Now, this has three. The first one is for copper, the second one, the straight line is for nichrome, the third one is for a semiconductor. So, first two are conductors, the third one is a semiconductor. In the first two conductors, when the temperature is increased, then the change in resistivity is not linear in the first graph. So, for copper, if the temperature is increased, then the resistivity increases rapidly, whereas for nichrome, when the temperature is increased, the resistivity is increased in a linear fashion. However, for a semiconductor, when there is an increase in the temperature, the resistivity will drop. So, what does that mean? When the temperature is increased, then the resistivity will decrease, it will start conducting. So, in the first two cases, the current will reduce in case if there is an increase in the temperature. However, the third case, if the temperature is increased, then the resistivity will reduce, as a result the current will increase. So, the semiconductor will start conducting when the temperature is increased. Now, again it is an important question, why when the temperature is increased, the resistivity also increases. The reason is, when the temperature increase, then the relaxation time tau decreases, and tau is inversely proportional to resistivity. So, when temperature is increased, the resistivity also increase because of this reason. This is again not a graph, but this is important. This shows dia and para. The top one is dia and the second one is para. So, this denotes that the magnetic fields actually pass through para, and dia, when we bring a magnet close to a diamagnetic material, it will actually get repelled. That is what is conveyed by this graph, by this figure. Now, in this, it simply gives the direction in which EMI is induced. If we take north pole close to a current carrying or a loop, then current will be induced in the anti-clockwise direction. So, this graph is why, again, this is important. This conveys the direction. So, if you observe, the anti-clockwise actually looks like N. So, N denotes anti-clockwise, and here the clockwise actually looks like S. So, if it is you can remember in this way, if it is south, then it means there is a decrease in the flux, or if the north is going away, or if south is coming in. All three can be considered as south. Okay, when the north is going away, or when the south pole is coming towards, or when there is a decrease in the flux. These three conditions, it will be clockwise or south. And when the north is coming in, the first scenario, south is going away, and when there is a flux increase. These three conditions, it will look, or the current induced direction will be in the anti-clockwise sense. And these two graphs are from the AC chapter. The first one, it denotes the voltage leads. So, this is voltage and this is current. So, the voltage leads current by 90 degrees. So, this is 90 degree. So, if you observe, the voltage is ahead of current. In this graph also, the blue color is voltage and this one is current. This one is current. So, the blue is voltage, red is current. So, there is a gap of pi by 2 and V is 90 degrees ahead of current in this graph. And the third one, do not be afraid of this or do not get scared. This also represents the same thing. Only difference, this also includes power. Whatever has been shaded, that is power. If you observe voltage, you may get a bit confused. In the first diagram, voltage started 0, but the second one, voltage started at 90 degree as cos. That does not matter. We just need to show, though the voltage is here, voltage starts like here like a cos wave, the current here represents a sine wave. So, cos is 90 degree ahead of sine. So, again this is an inductor where the voltage leads current by 90 degrees. And important aspect, in this graph both voltage and current completes one full cycle. If you observe, this is one full cycle for current, okay, whereas in this cycle power has completed 2 cycles. This is something which we need to know, because in exams they will give this graph and will ask us to identify which is voltage graph and which is current graph. So, the one which completes one full cycle in the given time period is current graph, and power graph will be completing 2 cycles in the same time duration. Again, this is capacitor. Here the voltage lags and the current leads. So, this one is the current, this leads the voltage by 90 degree. So, many students find this diagram confusing. It is very easy. So, if you observe, both I and V have a 90 degree phase difference here in this phasor diagram. This is like a vector diagram, and in this diagram also current starts as cos. So, we should be knowing that cos wave is 90 degree ahead of sine always. So, here the current represents a cos wave and voltage represents a sine wave. So, obviously voltage is 90 degree, voltage lags 90 degree current. The third one, it includes power, but again it represents the same. It is same as the previous one, voltage here and current here. and this diagram, it's resonance. In this from this diagram they may ask a question, which circuit has better quality factor. In case if they give you numerical values, and in case if they ask you which circuit has a higher quality factor, what is the formula for quality factor? It's L omega naught divided by R. So, quality factor has two formulas. One formula is L omega naught by R. This is also equal to 1 by C omega naught R. So, these two are the formulas. So, first formula is L omega naught by R, the other one is 1 by C omega naught R. So, in this graph, the one which is very sharp, so this formula is used to find the sharpness of the circuit. So, this one is very sharp, right. So, this one will have a higher quality factor. So, in questions they will give the L value, R value, omega naught, etc., and two sets of values, and they may ask which is a better circuit. So, which is a better circuit, whatever we can find the quality factor for both, and whichever circuit has maximum quality factor, that is a better circuit. And in these two graphs, there are two, one is pretty sharp, the other one is not so sharp. So, which of them is a better circuit? Obviously, the first one.